Okay, our first step is to connect the starting point, the initial point of the vector, through any of the points on our shape. And I'm going to start with point C. And we just extend through it because we're going to try and copy an angle, and we want to make sure we have enough space to do that. And the idea of what we're doing here is we are saying that if we have a line and we have a point somewhere else, to do a translation, we want to create a parallel line to the vector. And the construction we're going to use is our copying an angle construction, where we're going to copy an angle made to a transversal up to the point on our figure, and that will create parallel lines for us. Remember, these two angles are called corresponding angles because they are in the same position for two different figures. Once we do that, we take our compass and we're going to draw an arc that intersects both the vector and the transversal we just drew. And then we're going to go up to our point C and we're going to draw the exact same arc. And notice it's a little bigger on this side because we're going to try and find this point corresponding up here, and we don't know exactly where it is yet. So I'm going to mark in the first point of intersection, and I'm going to call that P, and I'm going to call the other one Q. And then up here, this is the copy of P, so this is going to be P prime, and we are looking for the copy of Q, which is Q prime. Our next step, set our compass to the segment between P and Q. So that is, we mark that length on our compass. We come up to P prime, and we swing that same length looking for where it intersects our first arc. And then we connect through. And what we should have, if we've done our constructions correctly, is we should have two parallel lines. So the vector, EF, should be parallel to the ray we just drew. And then the final part of our translation is to copy the length of the vector EF. So we set our compass to the vector length, we come up to C, and we mark that length on our parallel line that we just drew. So this will be the point C prime. After this, you have a couple of different things you can do. You can repeat the construction for all 3 points, or I'm going to show you a second method. And this is one where you're going to use a straight edge, and then you're also going to use what's called a set square. So a set square is one of our plastic triangles. We have a 90-degree angle, a 60, and a 30. The other one has two 45-degree angles. We're going to use the ruler as a straight edge, and it's going to act as a transversal for us. So in my case, you're going to see my ruler up the side here, and then we set the set square up to line up with our vector. So the idea is, if we treat the ruler as a transversal and the set square stays flush against it, when I move the set square, the edge still remains parallel to the vector itself. So I can use this to create parallel lines. So in the case up here, I'm going to do this for B. So I slide up to B, draw in my parallel line. So again, this line is parallel to the other two. Get my compass out, set it to the vector length, and mark it from B. And that is the location of my point B prime. So the first method, we are copying the angle. The second method, we're using a straight edge and a set square to create parallel lines. It's actually the same idea as what we were doing here, where we are saying if I have a straight edge that is making a fixed angle to a transversal, if I am still creating the same fixed angle at another point, it will create a parallel line for me. The third method requires using a little bit of properties of parallelograms. So we'll kind of give you a little sketch of that down here. And the idea is, if we have a parallelogram, what we know about parallelograms is opposite sides are parallel, but also opposite sides are equal in length. And the theorem is if you have opposite sides in a four-sided figure equal in length, that the opposite sides must also be parallel. So it's one of our theorems about parallelograms. The converse, or the opposite of that, is also true. If you have opposite sides of equal length, they must be parallel, and then if opposite sides are parallel, they must be equal in length. So both statements are true. We're going to use that here, and in my diagram, basically, the base of this parallelogram is our vector EF, and the point I'm going to use for this one is point A. So I know three of the points on my quadrilateral, my parallelogram, and the idea is if I copy the lengths for opposite sides, that the point I will get from their intersection will complete the parallelogram and will also be the same length and parallel to the vector. So first step, I'm going to use my compass and measure the length of the vector, and I'm going to swing that length from point A. So this is the equivalent of me saying, okay, I know the length of EF, I'm going to go to A, swing that length, so I know that A prime is going to be that distance away from A as well. The second step is to go to point E, set your compass to the distance from E to the point in the shape, in my case A, and then come down to the end of the vector, the terminal point, and swing that same length. So this is me saying I know the distance from E to A, and if I make the same distance on the opposite side of the parallelogram, I'm going to end up with a point of intersection that completes the parallelogram.
Teachers and students, please pardon this interruption. Due to the impending weather forecast.
Okay, the final part of the video got cut off there for a second, but all I did was I finished with my compass method, so marked my points of intersection, got the point A prime, and then connected my figure and shaded in just to show the final image.